I'm going to tell you how to train a neural network to solve a multi-class classification problem. And in the process, I'm going to tell you a recipe, a general recipe that we can use to develop a multi-class classification algorithm. As an example of a multi-class classification problem, I'm going to use the classic iris dataset. There are three types of irises in this data set called setosa, versicolor, and virginica. And for each iris in the data set, we have four measurements, four numbers: petal width, petal length, sepal width, and sepal length. So for each iris in this data set, we have a list or a vector containing these four numbers. These four numbers are sometimes called features, and this vector is sometimes called a feature vector. And in this data set, we have 150 irises. So for each of those 150 irises in the data set, we have a vector, a feature vector, containing these four measurements: petal length, petal width, sepal length, sepal width. Our goal is to create an algorithm which can take as input a feature vector describing a particular iris and give us as output a prediction for which class this particular iris belongs to. Is it a setosa, is it a versicolor, or is it a virginica? There's three possible classes in this data set. Before we get started, I first have to tell you a definition. I'm going to define a probability vector to be a vector whose components are non-negative. The components of the vector are non-negative and they add up to 1. It doesn't have to be a vector with 3 components. It could be a vector with 10 components or with 100 components, or in general, a vector with k components. But in this example, our probability vector has 3 components. And if we're doing a multi-class classification problem with k possible classes, in this case, k is equal to 3, I will often think of each component of my probability vector as telling me how likely the example I'm looking at is to belong to each of the possible classes. So this probability vector is telling me that there's a 30% chance the example we're looking at belongs to class 1. There's a 60% chance that the example we're looking at belongs to class 2. And there's a 10% chance that the example we're looking at belongs to class 3. So in the opinion of this probability vector, the example that we're looking at is most likely to belong to class 2. Here's another example of a probability vector: 0, 1, 0. This is a probability vector that expresses certainty about which class you belong to. According to this probability vector, there's a 0% chance that you belong to the first class. There's a 100% chance that you belong to the second class, and there's a 0% chance that you belong to the third class. So this probability vector expresses certainty. Another example could be the vector 0, 0, 1. This probability vector tells us with 100% certainty that you belong to class 3. So there's a 0% chance you belong to class 1, a 0% chance you belong to the second class, 100% chance you belong to the third class. So remember, there are 2 requirements that must be satisfied for a probability vector. Each component must be non-negative, and the components of the probability vector must sum to 1. And now we're ready to learn our recipe for a multi-class classification algorithm. The first ingredient in our recipe for a multi-class classification algorithm is a training data set. We need to go out into the world and collect some data. And our training data set is going to consist of a list of feature vectors. The first feature vector is called x1, the second feature vector is called x2, and so on. So for example, for the iris data set, our first feature vector describing our first iris might be, for example, 0.8, 0.7, 1.4, 1.8. I just made those numbers up. And our second feature vector describing the next iris in our data set might be 0.9, 0.6, 1.3, 1.5. Again, I just made these numbers up, and so on. And then for the iris data set, capital N is equal to 150, because we have 150 irises in the iris data set. And lowercase d is equal to 4 because each feature vector is a vector in R4 for the iris data set. And along with our feature vectors, we also need to be given corresponding target values called y1, y2, and so on, all the way up through y capital N. This target value is going to be a probability vector which expresses certainty about which class this iris belongs to. So for example, this first target vector might be 0, 1, 0. This is a probability vector that tells us with 100% certainty that the first iris in our data set belongs to the second class. The position of the 1 tells you which class you belong to. And so, for example, y2 might be the probability vector 0, 0, 1. This probability vector tells us with 100% certainty that the second iris in our data set belongs to the third class. The position of the 1 tells you which class you belong to. And notice that each target vector is a vector in R capital K. Here, capital K is the number of possible classes in our classification problem. So for the iris data set, capital K is 3. We have 3 possible classes. The next ingredient in our recipe is a prediction function. I'm going to call the prediction function f. F is a function from Rd to Rk. Our prediction function should take as input a feature vector which describes a particular iris, for example, and the output should be a predicted target vector for the particular iris that we're looking at. So the output of f should be a probability vector. The output of f should be a probability vector. And here's our hope for the prediction function. What we hope is that if we take any feature vector in our training data set and plug it in to our prediction function f, what we're going to get is a predicted target vector which agrees closely with the ground truth target vector from our training data set. And we hope that this will be true for each example in our training data set. And you could say that the main goal of machine learning, or at least one of the major goals of machine learning, is to find a good prediction function that makes good predictions. And the question that might occur to you is, what form should we assume for the prediction function? What form should we assume for the prediction function? In other words, what formula should we use for the prediction function? And this is one of the major questions of machine learning. Much of machine learning can be viewed as just getting creative about the formula that we use for f, getting creative about what form we assume for f. So f could be a linear function, or it could be a decision tree, or it could be a neural network, or there's other options. So a whole lot of machine learning fits into the recipe that we're describing. And to get started, let's ask ourselves, what is the simplest formula that we might assume for f? What is a very simple choice for the form of f? Well, let's start by trying something very simple. How about our prediction function f takes as input a feature vector xi. It takes the feature vector and it multiplies it by a matrix B, and then it adds a vector that I will call lowercase b. And then how about that? Is this going to give us a good prediction function? Remember that this vector x sub I belongs to Rd, so it is a d by 1 column vector. This matrix B should be capital K by D. That should be the shape of this matrix capital B. And then this vector B should be a K by 1 column vector. Does this formula give us a good prediction function? Well, there's one problem with this formula that we can see immediately. Remember, we said earlier that the output of our prediction function should be a probability vector. And there's nothing to guarantee that this vector is going to be a probability vector. There's no reason to expect that the components of this vector should be non-negative, and there's no reason to expect that the components of this vector should sum to 1. So that's a problem. And how can we fix that problem? In order to fix that problem, I'm going to tell you about a function which is called the Softmax function. I'm going to use the letter capital S for the Softmax function, and it's capital S is a function from Rk to Rk. The purpose of capital S is to convert a generic vector in Rk into a probability vector. And let's see how it's going to do that. The input to S can be any vector in Rk. I'm going to call this vector U. This is a generic vector in Rk. This vector U may not be a probability vector for 2 reasons. Reason 1, some of the components of U might be negative. How can we fix that? Well, one way to fix that is to apply the exponential function to each component of U. So that gives us e to the U1, e to the U2, and so on. And finally, e to the U capital K. And now each of these numbers is non-negative. In fact, when e to any power is always positive. So that is progress towards constructing a probability vector. So now the components of this vector are non-negative, but we still have a problem, which is that the components of this vector may not sum to 1. The sum of the components of this vector is e to the U1 plus e to the U2 plus ... plus e to the UK. And there's no reason to expect the sum to be equal to 1. So how can we fix this problem? Well, why don't we just scale this vector by 1 over this number? So the first component will get divided by e to the U1 plus ... plus e to the UK. And the second component will also get divided by e to the U1 plus ... plus e to the UK, and so on. And the final component will also get divided by e to the U1 plus ... plus e to the UK. And now the components of this vector do sum to 1. So this is a genuine probability vector. The whole purpose of the softmax function is that it takes as input a generic vector in Rk, and it converts it into a probability vector. Let's double check that the components of this vector really do add up to 1. What happens when we add up the components of this vector? Well, we already have a common denominator. We have a common denominator already. And what's the numerator going to be when we add up all these components? Well, it's going to be e to the U1 plus e to the U2 plus ... plus e to the UK. The numerator turns out to be the same as the denominator. And so the sum of the components of this vector is 1. The softmax function is very useful in machine learning because it can convert any vector you want into a probability vector. And you might be thinking, are you sure there's no simpler way? Are you sure there's no simpler function that does this job for us, that can convert any vector into a probability vector. And I claim that if you try to find a simple function that does this job for us, converting a vector into a probability vector, and if you want this function to be differentiable, a differentiable function, I don't think it gets much simpler than that. I think this is about the simplest formula we can come up with that does the job. So now returning to our earlier question of what form should we assume for our prediction function, and here we're trying to think of something very simple. So the simplest thing we tried was just take our feature vector as input, multiply by a matrix, add a vector. That's very simple. The problem with this formula is that this result is not guaranteed to be a probability vector. We can fix that problem just by applying the softmax function to this vector. And then the output of this prediction function is guaranteed to be a probability vector, and that's what we want. So this is one of the simplest possible choices for our prediction function. This is the form that we assume for f when we do what is called multiclass logistic regression, which is one of the simplest and most classical algorithms for multiclass classification. And by the way, this function f, I often call it a prediction function. Another term you hear a lot in machine learning is model. This function f is often called our model, but I will more often call it a prediction function. And remember that this is a very simple choice for f, for the form of f. We could get much more creative. For example, f could be a neural network. And much of machine learning is just getting very creative about what form we assume for f. Now that we've decided what form to assume for our prediction function, what form to use for our prediction function, we're now faced with another major question. How do we choose the matrix B? And how do we choose this vector lowercase b? The entries of this matrix capital B and the entries of this vector lowercase b, these are called the parameters for our prediction function, or the parameters of our model. And one of the major questions that we have to answer in machine learning is, how do we find good values for the parameters of our model? How do we make a good choice or an optimal choice for this matrix capital B and this vector lowercase b? If we choose good values for the parameters of our prediction function, then we're going to get a good prediction function that makes good predictions, accurate predictions. And if we make bad choices for the parameters of our model, then we're going to get a bad prediction function that makes bad predictions. For example, if the matrix capital B were chosen randomly and the vector lowercase b were chosen randomly, there's no reason to expect that our prediction function would make good predictions. So I'm going to describe a strategy that we can use to make good choices for the parameters for our prediction function. Now remember our hope. Our hope is that for each feature vector in the training data set, our predicted probability vector agrees closely with the ground truth probability vector. In order to make this more precise, we need a way of measuring or quantifying how well a predicted probability vector agrees with a ground truth probability vector. And this brings us to the next ingredient in our recipe for a multi-class classification algorithm. Our next ingredient is what is called a loss function. And I'm going to call the loss function lowercase l. The job of the loss function is to measure or quantify how well a predicted probability vector Q agrees with a ground truth probability vector P. P and Q are going to be the inputs to our loss function. And if the predicted probability vector Q, if it agrees well with P, the ground truth probability vector, then L of PQ is going to be small. And if Q does not agree well with P, then L of PQ is going to be large. So L of P comma Q will be small when Q agrees well with P. And now we are faced with another question. This is another one of the fundamental questions in machine learning. What should we use for the loss function? How can we possibly quantify or measure how well a predicted probability vector Q agrees with a ground truth probability vector P? Well, here's one idea, and this is maybe the simplest idea we could think of. Why don't we define L of P comma Q to be just the distance between P and Q? How about that? If we visualize P and Q as points in space, then P minus Q is the displacement vector from Q to P, and then we're taking the norm or the length of that displacement vector. So this is just computing the distance from Q to P. And if we write P and Q in more detail by writing their components explicitly, then we can write this formula in more detail. So the norm of P minus Q is equal to the square root of P1 minus Q1 squared plus dot 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 plus PK minus QK squared. This seems like a reasonable choice for a loss function. If Q agrees perfectly with P, then L of PQ is 0. If Q does not agree well with P, then L of PQ will be very large. This square root sign makes the math work out less nicely, or it makes the math more difficult. So we typically square the norm of P minus Q. So instead of choosing our loss function to be just the norm of P minus Q, we're instead going to use the norm of P minus Q squared to make the radical go away. And this loss function is called the squared error loss function. This is the loss function that we typically use when we're doing regression, but it turns out to be not the loss function that we typically use when we're doing multiclass classification. When we're doing multiclass classification, we typically use a different and actually stranger looking loss function, which is called the cross entropy loss function. And cross entropy loss function is one of those names in math that is probably unnecessarily intimidating. In fact, the engineer Shannon discovered a related quantity, and he was considering calling it something like information or uncertainty, which is a more illuminating name. And he asked the mathematician von Neumann what he should call this quantity. And von Neumann said, you should call it entropy for 2 reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name. In the second place, and more importantly, no one knows what entropy really is. So in a debate, you will always have the advantage. It's a bit hard to motivate where the formula for the cross entropy loss function comes from. So first, I'm just going to write the formula down. The inputs to the cross entropy loss function are a predicted probability vector called Q, whose components are called Q1 through Qk, and a ground truth probability vector called P, whose components are called P1 through Pk. And the cross entropy loss function is defined like this. L of P comma Q is equal to minus P1 times the natural log of Q1 minus P2 times the natural log of Q2 minus dot 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 minus P sub k times the natural log of Q sub k. Admittedly, this is a strange looking formula, but it turns out that this function has the properties that we want our loss function to have. If Q agrees well with P, then the cross entropy value is small. If Q does not agree well with P, then the cross entropy value is large. It's also possible to show that for any given probability vector P, if we want to choose Q to make this quantity as small as possible, the best choice that we can possibly make is to choose Q equal to P. That is the value of Q that minimizes this quantity. I'm not going to give a proof of that fact, but it might be illuminating to look at the special case where P has a 1 in the first position and zeros elsewhere. So P is, in this case, P is a probability vector that expresses certainty that the example we're looking at belongs to class 1. In this special case, L of P comma Q is equal to minus log of Q1 because P1 is equal to 1. And then this term is 0 because P2 is 0. All the remaining terms are 0. So in this special case, L of PQ is just equal to minus log of Q1. Now, how can we choose the probability vector Q to make this quantity as small as possible? And keep in mind that the components of Q have to be in between 0 and 1 because Q is a probability vector. If Q1, the first component of Q, is less than 1, then the natural log of Q1 is going to be negative, and so minus natural log of Q1 will be positive. However, if Q1 is actually equal to 1, then the natural log of Q1 will be 0, and this quantity will be 0. So the best choice of Q to make this quantity as small as possible is to choose Q1 to be equal to 1 and to choose the remaining components of Q to be all 0. With that choice of Q, the cross entropy value turns out to be 0, which is as small as we can possibly make it. So in this special case, where P is the vector 1, 0, 0, the choice of Q that minimizes the cross entropy value is to choose Q equal to P. This helps to demonstrate that our strange-looking cross-entropy function has the behavior that we hope for when choosing a loss function. But I still haven't explained where this strange-looking formula comes from. How would somebody think of this formula? I'll make one comment about that. If you're familiar with maximum likelihood estimation from statistics, it's possible to take a statistical viewpoint and use the maximum likelihood estimation technique to estimate the parameters of our model. And if you do that, and if you work out all the details and do the math, then the cross entropy loss function will emerge from that calculation. It will pop out from the details of that calculation. And I think that is probably the most straightforward way that someone might discover the cross entropy loss function. Even though this formula looks strange at first, this is in some sense, in some mathematical sense, the most natural or the most beautiful way to measure how well a predicted probability vector Q agrees with a ground truth probability vector P. And so this is the loss function that we will typically use when doing multi-class classification. Now that we've chosen our loss function, we're ready to return to our earlier question, which was, how do we choose good values for the parameters of our model? How do we make a good choice for this matrix B? How do we make a good choice for this vector B, or ideally a choice which is optimal in some sense? Remember, our hope is that for each example in the training data set, our predicted target value, our predicted probability vector, will agree closely with the ground truth probability vector. And we hope that this is true for each example in our training data set. To make this more precise, we want the cross entropy value to be small for each example in our training data set. We want the cross entropy value to be small because if our predicted probability vector agrees closely with our ground truth probability vector, then the cross entropy value will be small. And we hope this is true for each example in the training data set. Another way to say this is that if we compute the average cross entropy, averaging all the cross entropy values for all of the examples in the training data set, that average cross entropy value should be small. I'm going to call this average cross entropy value capital L. And keep in mind that this average cross entropy value depends on the values of capital B and lowercase b. It depends on the parameters of our model. If we were to change capital B or change lowercase b, we would get a different prediction function that makes different predictions and the average cross entropy value would change. So capital L depends on the parameters of our model. And to remind us of that, I'm going to write capital L as a function of beta, where beta is a vector that contains all of the parameters of our model. This vector beta contains all of the entries of B and all of the entries of lowercase b. You could imagine they're all just written as a big list of numbers. So all of the parameters for our prediction function are stored in this vector beta. And now we can see a strategy for choosing good values for the parameters of our model. We're going to choose the parameters for our prediction function in order to minimize the average cross entropy value. In other words, we're going to choose the entries of the matrix capital B and the entries of the vector lowercase b in order to minimize the average cross entropy value. So this means we're going to choose the parameters for our model by solving an optimization problem. We are going to choose the parameter vector beta in order to minimize capital L of beta. This function, capital L, is called our cost function, or sometimes it's called the objective function. It is the function whose value we want to minimize. And the process of finding a vector beta which minimizes capital L of beta is called training our model. If you've ever heard of people training a neural network, this is what it means. We are choosing the parameters of our model to minimize the average cross entropy. This cost function, capital L, is the next ingredient in our recipe for a multi-class classification algorithm. This isn't the only possible choice for capital L. It's possible to get more creative with this ingredient and choose different cost functions, but this is the most popular and the most common cost function that is used for multi-class classification. You might be wondering, how can we possibly solve this optimization problem? How can we possibly find a parameter vector beta which minimizes L of beta? In single variable calculus, we learned how to minimize functions, and we do it by setting the derivative equal to 0. So you might wonder if we could do something similar here. Can we just take the derivative of L and set it equal to 0? And that's not a bad idea, but we have to ask ourselves, what do we even mean by the derivative of L? Because L is a function of several variables. L is a function of many variables. This parameter vector beta is a long list of numbers. So that means the question of how to define the derivative of capital L is a question about multivariable calculus. And if you've taken multivariable calculus, then you might have learned that there is something called the gradient vector for L, which is analogous to the derivative that we learn about in single variable calculus. And it does turn out to be true that if the vector beta minimizes capital L, then the gradient of L at beta is equal to 0. So we could attempt to set the gradient of L equal to 0 and then solve for beta. However, the system of equations that we obtain when we set the gradient of L equal to 0 is a nonlinear system of equations. It's a large system of nonlinear equations, and it might be difficult to solve. So instead of taking that approach, we're going to take a different approach. And we're going to minimize L using an algorithm called gradient descent. Gradient descent is one of the most fundamental and one of the most famous optimization algorithms. The goal of gradient descent is to find a vector beta which minimizes a smooth function capital L. In order to explain how gradient descent works, I first need to explain what the gradient vector is. When I'm thinking about the gradient vector, what I like to imagine is that capital L is a function which tells me the temperature at each location in space. And then at each location in space, it is possible to compute a vector called the gradient vector. And the gradient vector points in the direction for which the temperature is increasing most rapidly. In other words, at any given location in space, the gradient vector is a vector which points in the direction for which the function capital L is increasing most rapidly. The gradient vector points in the direction of steepest ascent for capital L. And the magnitude or the length of the gradient vector tells us how rapidly the function L is increasing in that direction. It tells us how rapidly the temperature is increasing in that gradient direction. So let's imagine that we're standing in a room and there's a fire burning over on the right, and there's a big block of ice over on the left. At any point in space, we can compute the gradient vector. So if we compute the gradient vector at this location, it's going to be pointing to the right, pointing at the fire, because that is the direction in which the temperature is increasing most rapidly. If we were to compute the gradient vector at this location, it would again be pointing at the fire, pointing in the direction of steepest ascent for our function L for the temperature. If we were to compute the gradient here at this location, it would again be pointing in the direction of steepest ascent. At every possible point in space, there is a gradient vector which we could compute. So how does this gradient vector help us to solve an optimization problem? Imagine that there's a mosquito flying around in space, and the mosquito likes cold temperature. So the mosquito wants to find a location for which the temperature is very cold, in fact, as cold as possible. That means this mosquito wants to solve an optimization problem. It wants to minimize the temperature. Here's a strategy that the mosquito can use. Let's say the mosquito is initially located at this location. The mosquito is going to compute the gradient vector for capital L at the mosquito's current location. So the gradient vector points to the right. Now the mosquito knows that the temperature is increasing most rapidly in this direction. So what should the mosquito do? The mosquito is going to move in the opposite direction. That's the opposite direction, the negative gradient direction. That's the direction in which the temperature is decreasing most rapidly. So the mosquito is going to move a short distance in the negative gradient direction. And now this is the mosquito's new location. Okay, so now the mosquito is going to compute the gradient vector again. And once again, the mosquito is going to take a short step in the negative gradient direction, which is the direction in which the temperature is decreasing most rapidly. And the mosquito just keeps doing this again and again. It computes the gradient vector at its current location. It takes a short step in the negative gradient direction. Every time it takes one of these little steps, the temperature is reduced. And the mosquito keeps doing this again and again, step by step, until eventually the mosquito reaches a location where the temperature can be reduced no further. And at that point, the mosquito is done. The mosquito has found a location where the temperature is as cold as possible. This strategy for solving an optimization problem is called the gradient descent algorithm. And we can use this strategy, this algorithm, to minimize our cost function, capital L. That is how we're going to find the parameters for our prediction function. There is a certain notation that mathematicians use to write the gradient vector. If beta is a particular location in space, a particular point in space, then the gradient vector is written like this. In math notation, we use this upside down triangle symbol when we're writing the gradient vector for L at a given point beta. And with this notation for the gradient vector, we can write the gradient descent algorithm using math notation. So suppose that our current location is called beta. Then what we're going to do is compute the gradient vector for L at our current location. And then starting from our current location, we're going to take a short step in the negative gradient direction, and that's going to give us our new updated location. So starting from our current location beta, we take a short step in the negative gradient direction, and that gives us our new updated location. And in the gradient descent algorithm, we just keep doing this again and again until we converge to a minimizer for capital L. We keep taking short steps in the negative gradient direction until finally we arrive at a location where the temperature can be reduced no further. This number alpha is called the learning rate for the gradient descent algorithm. And it's up to us to choose the value for alpha. Often the value of alpha is chosen by trial and error. Maybe a value such as 0.01 or 0.001 might be typical, but the best value for alpha depends on the data that you're working with. If alpha is large, that means we're taking large aggressive steps, and we might expect to converge to a minimizer faster. There's a problem though, which is that if alpha is too large, then the gradient descent iteration might not converge at all. The mosquito might find that he is just flying off into space if his learning rate is too large. But there is a mathematical guarantee that the gradient descent iteration will converge if the learning rate is sufficiently small. On the other hand, if the learning rate alpha is chosen to be too small, then that means we're taking very tiny, very conservative steps, and we will move very slowly. We will converge very slowly to the minimizer, and that might be too slow. It might take too long. So when we're using the gradient descent algorithm, we need to find, perhaps by trial and error, a value for the learning rate alpha, which is small enough that the algorithm converges, but not too small. And people have come up with clever algorithms where the learning rate alpha is chosen adaptively so that we use a different learning rate at each step, at each iteration of gradient descent. But in the simplest version of gradient descent, we just use a fixed learning rate. If you're trying to use the gradient descent algorithm to minimize a function capital L, the hardest part of implementing this is to actually compute the gradient vector. And I haven't said how to do that. How do we actually compute the gradient vector? That's a big question. And if you take a course on multivariable calculus, you learn all kinds of techniques for computing the gradient vector. You could imagine that in machine learning, computing the gradient for this cost function, capital L, might be a pretty complicated calculation. If you try to do the whole calculation on paper using techniques from multivariable calculus, like the chain rule, for example, it might be a rather complicated calculation. But the good news is that when we train a neural network, we're going to use a library called PyTorch, and PyTorch is going to be able to compute the gradient vector for us. So we're not even going to need to worry about how to compute the gradient vector, how to do the math involved in computing the gradient vector. PyTorch is just going to handle that for us.